Hello everyone, my name is Swayam Prabha. I am a PhD student in the Department of Electrical Engineering, IIT Bombay. So today I am here with you all to discuss a very important concept from linear algebra which is directly applicable to wavelets. And this concept is popularly known as the concept of direct sum of vector spaces. Now I will be giving you the definition of as to what this operation is, and I will be giving you two examples. One example will be from finite dimensional vector spaces and another example will be from infinite dimensional vector spaces. Then let us proceed to the definition of this operation. Okay. So definition, suppose V is a vector space and V1 and V2 are two subspaces of V such that by S dot T dot I mean such that V1 intersection V2 is just the 0 vector. Then if this is true, this is a very important thing in this definition. If this thing is true, then we say that V is a direct sum of V1 and V2 if any vector x in V can be represented as x equal to x1 plus x2, where x1 belongs to the set V1 and x2 belongs to the set or vector subspace V2. So there are few important things which I would like to dwell upon for a second, that for defining the direct sum we need to have this thing very precise, that two subspaces that are involved in the direct sum should have 0 intersection, or they should have only origin of that vector subspace as their common point. Now let us look at two examples from finite dimensional vector spaces and one example from infinite dimensional vector spaces. So in finite dimensional vector space, let us look at our Euclidean two-dimensional plane, which is also popularly represented as R2. So it is our normal Euclidean two-dimensional plane. Now let us consider two subspaces of this Euclidean space. One subspace, let me call it as span of the vector 1 0. Now in this two-dimensional vector subspace, by saying that V1 is a span of 1 0, what do I mean is that 1 comma 0 is this point. So I am representing it as a column vector, and by span means that I am allowing any scalar multiplication. Okay, by span means any vector which is of the form alpha times 1 0, where alpha is any real number. So if you think on this for a second, you will realize that I am talking of this whole real axis which runs from minus infinity to plus infinity. And let us consider another vector subspace which is given by span of 0 comma 1. So similarly, the span of 0 comma 1 will be the vectors which lie on this y axis or the vertical axis. Now as we can see that if I consider any point x y in this R2 or in my two-dimensional Euclidean space, then I can write this point x y as x times 1 comma 0 plus y times 0 1. So for any real number x and y, I have shown that any point in R2 can be written as a scalar times 1 0 plus a scalar times 0 1. So this first part, as we can see that this part belongs to V1 and this part belongs to V2. Now all that remains to show is that the only point which is common to both V1 and V2 is nothing but the origin of the two-dimensional Euclidean space. So, we will show it now. Let us suppose that there is a point x1 comma y1 which lie in the intersection of V1 and V2. This implies that if x1 belongs to V1 intersection V2, then this point x1 comma y1 should belong to V1 and x1 comma y1 should belong to V2. But if x1 comma y1 belongs to V1, then from here we have another implication that x1 comma y1 is of the form some scalar times 1 0, and from here we have the implication that x1 comma y1 is of the form beta times some scalar beta times 0 1. So, from here I have actually this point has to satisfy 4 simultaneous linear equations. And what are those 4 simultaneous linear equations? This is true and this is also true. So, 4 simultaneous linear equations that my point x1 y1 has to satisfy are x1 is equal to alpha, y1 is equal to 0 and x1 is equal to 0 and y1 is equal to beta. So, simultaneous word is very important here. You know, this point x1 y1 has to simultaneously satisfy all these 4 equations. Now, when this can be true, if and only if alpha comma beta both the reals are 0, that is my point x1 y1 is nothing but the origin in R2. So, what we have essentially shown here that my R2 is the direct sum of span 1 comma 0 and span of 0 comma 1. Very simple. Now, I would like to point a very important subtlety in the case of finite dimensional vector spaces. When we talk of finite dimensional vector spaces, it is important that the two subspaces which are involved in the operation of direct sum should be such that dimension of those two subspaces should add up to the dimension of the whole space. For example, when we were talking about R2, we saw that R2 is the direct combination of this subspace and this subspace, and these two are one dimensional subspaces, and the dimension of these two subspaces add up to 2, which is the dimension of the whole R2. So, this is an important subtlety in the case of finite dimensional vector spaces. Now, let us take an example from infinite dimensional vectors. Now, this is very interesting. Let us consider a subspace V which is set of all the functions f from R to R. I am considering a subspace V which is a set of all the functions from R to R. Now, let us define two other subs. This symbol means I am defining V to be this set. Now, let us define two more subspaces. One subspace is V1, which is the set of all the functions f1 such that f1x is equal to f1 of minus x. Okay. So, this is the subspace of all the even functions. I am defining another subspace V2 of all the functions f2 such that f2x is equal to minus 2 of minus x. So, this is the set of all the odd functions. Note here that in both these cases x, I am talking about x in R. So, what I will be showing that any function which is of mapping from real number to real number is actually a direct sum of functions from set of even function and a function from the set of odd function. So, let us show that. Now, consider a function g of x. Now, here g I am taking as an element of v. Now, we know that any g can be written as half times g1x plus g2x, okay, where g1x is equal to g of x plus g of minus x, and g2x is equal to g of x minus g of minus x. Now, this is a very elemental thing that we all must have studied in our basic calculus course. So, note here that g1 is an even function, because if in the place of x we go ahead and substitute minus x, then what we will get is g1 of minus x is g of minus x plus g of minus x, which is g of x, which is again equal to g1 of x. So, this part is even function. By EV I mean function even, and this part can therefore be shown as an odd function. Now, what we have shown here, that any element of V of the vector subspace V can be represented in the terms of element from the vector subspace V1, which is G1x, and element from the vector subspace V2, which is G2x. Now, for showing that this is actually a direct sum, okay, what remains to show is that the only function which is common to both V1 and V2 is nothing but zero function. Okay. So, what is zero function? Zero function is a function which for all the argument x gives you the value 0. This is a zero function. So, let us take a function f which is in the intersection of V1 and V2. So, if f is in the intersection of V1 and V2, this implies that f belongs to V1. This is true, then this implies that f of x is equal to f of minus x. And if f belongs to intersection of these two subspaces, then this also implies that f is in V2, which implies that f of x or f of minus x is nothing but minus f of x. So, what do we have here? We have here basically these two equations. Now, these two equations, if you look at closely, then these two equations are true if and only if 1 and 2 are simultaneously true. This simultaneously word is very important. These two equations are simultaneously true if and only if f is your zero function, which we have earlier defined. So, what we have shown here is that any function which has its domain as a whole real line and its range as a whole real line can be written as the addition of two functions which are even and one of them is odd. Okay. So, now this direct sum operation, I think if you all want to read about it more, then you can, there are various books on linear algebra actually which you can consult. One of the very good books which I find very interesting for beginners is Linear Algebra and its Application. This is the book by Gilbert Strang. It is available in low price edition in PHI publication. So, we can also buy it if you want. Another very good book which I find interesting is Sheldon Exler, Linear Algebra Done Right. I think it's available with Springer. And the third and very important book which I would recommend you all to study very thoroughly is Huffman and Kunz. Its name is just Linear Algebra. It's also available in low price edition with PHI. Thank you very much.